Hello students, I hope you all are doing good. Today we are going to study chapter wave optics. In this lecture we will cover NCERT section 10.5 in this lecture. So this is the disclaimer. So after this lecture you will be able to understand the theoretical principles of geometry of Young's double slit experiment. We focus on understanding the path difference, calculations and approximations. This is important because the path difference determines the type of interference pattern we observe. Next, we will explore how constructive and destructive interference occurs in this experiment. So you will be able to learn how the constructive and destructive interference occurs in Young's double slit experiment. And you will be able to calculate and predict where bright and dark bands or fringes will appear on the screen. So in this lecture, we are going to cover 10.5 section of NCERT, that is interference of light waves and Young's experiment. So now students, let's start with the interference using light waves. Our objective is to understand interference, and interference is a fascinating phenomenon where two or more waves overlap and combine to form a new wave pattern. This concept is crucial in wave optics and helps us understand various optical phenomena. So let's take a look at figure 10.11. Here you need to point out that how two sodium lamps are used to illuminate two pinholes, labeled S1 and S2. This setup is crucial for our discussion on interference. Pay attention to how the light from these lamps interact. So in this setup, we use two sodium lamps to illuminate the pinholes. We won't observe any interference fringes on the screen. So this is an important observation because it highlights the conditions under which interference pattern do not form. So we won't see any alternating bright and dark strips, that is known as interference pattern. What is interference pattern? That is alternating bright and dark stripes, or we can say fringes, on the screen. We will not see that pattern. So this absence of a pattern is key to understanding the behavior of light in this setup. So reason we don't see an interference pattern is that regular light sources like sodium lamps change their phase very quickly. This rapid phase change prevents the formation of stable interference patterns. We have discussed that when two coherent sources are taken, then interference pattern is formed. Due to the coherent sources at any point P. We have discussed in our yesterday class, due to two coherent sources at any point P, the phase difference between the waves originating from that two coherent sources is not changing with respect to time. So phase difference is constant, due to which at P point either it will be destructive interference or constructive interference. Either it will be dark strip or bright strip. But if we are taking two independent sources, we have discussed also that two independent sources are incoherent, due to which phase at any point changes very quickly, and phase difference between the waves originating from that two independent sources at any point will be changing with respect to time very rapidly. So the interference pattern, the position of the dark and bright fringes changes very rapidly, that our eye cannot detect that change. That rapid of change, that our eye cannot detect it. So we cannot see the interference pattern if we are using two incoherent sources or two independent sources. So these phase changes occur extremely fast, approximately every 10⁻⁻10 seconds. This rapid change is too quick for our eyes to detect any interference pattern, which is why we see a uniform intensity instead. So let's examine why light waves from two independent sources like our sodium lamps don't create interference patterns. So these sources are incoherent, meaning they don't have fixed phase relationship. Means at any point the waves originating from these two independent sources, okay, they have their phase changes quickly. So phase difference will also change rapidly at any point. Okay, meaning they don't have fixed phase relationship. This incoherence is why the light waves don't combine to form interference fringes. It's important to recognize that coherence is a key factor to interference. Now let's consider what happens with incoherent light sources. When these sources illuminate a screen, the light intensity simply add up. We have discussed yesterday also. Okay, so we will see the pattern with uniform. We will not see any pattern, or we will see the screen illuminated with uniform intensity. At that intensity is averaged over the intensity of individual waves. Okay, so that is I equal to I1 plus I2. I1 and I2 is the intensity of waves produced by S1 and S2 respectively. Okay, so the intensity will simply add up, representing by equation I equal to I1 plus I2. This means that instead of seeing interference pattern, we will see a uniform intensity. The screen will be illuminated, but with uniform intensity, not with dark and bright fringes or pattern, any pattern. Okay, so instead of seeing interference pattern, we will just see a uniform intensity. This reinforces the idea that coherence is necessary for interference to occur. So let's start by talking Thomas Young, a British physicist. Okay, notice how his name is highlighted in blue. Okay, so Young was instrumental in developing a method to study light waves. So he came up with a creative idea. Okay, his work laid the foundation for understanding how light waves can interfere with each other. He verified the concept given by Huygens. Okay, Huygens explained the reflection and diffraction with the help of wave nature. He proposed that light is a wave. Okay, light has wave nature. So he verified with that experiment by showing the interference pattern. Okay, so Young's method was ingenious because it allowed light waves from two sources to remain in sync, or we can say in same phase. This synchronization is crucial for observing interference pattern. Okay, so to achieve this, Young used an opaque screen, which is a material that light cannot pass through. Okay, this arrangement was key to producing the interference pattern we will explore. Now you will see figure 10.12, Young's arrangement to produce interference pattern. So he uses opaque screens, that is first screen, second screen. You can see three screens. So in first screen, there is only one hole and we called it as slit. Okay, small pinholes. And in second screen, there is two pinholes, two slits, S1 and S2. And third screen is placed to see the interference pattern, alternating dark and bright fringes. Okay, and on the right hand side, the diagram is showing two slits and a P point where we want to see which fringe is formed. Will there be constructive interference or destructive interference at P? We will see both cases. Okay. So in figure 10.12, you can see Young made two tiny holes in the screen labeled S1 and S2. These holes were placed very close to each other. Their separation is very, very, very small. Okay, in the terms of millimeter. This setup allowed light to pass through these points and create the condition necessary for interference. So before these two holes, Young placed another pinhole labeled S with a bright light source behind it. Okay, so he took a source. Okay, so to illuminate the slits, okay, he need the light source to form the interference pattern. So behind this screen with one hole, with one pinhole S, he placed a bright source. Okay, and this initial pinhole ensured that light reaching S1 and S2 was coherent. Okay, so a very thin beam of light will be emerging from S. Okay, it is falling on S1 and S2, and due to S1 and S2, so this S will behave as single source. Okay, and light coming from S1 and S2 will behave as in phase, means the waves that are that are originating from S1 and S2 slit will be having same phase difference at any point. And phase difference at any point due to waves originating from S1 and S2 will not change. Mean S1 and S2 are coherent sources. Okay, so that pinhole S will ensure that S1 and S2 are coherent, meaning it had a consistent phase relationship, or we can say constant phase difference. Okay, which is essential for interference. Okay, so before these two holes, he placed another pinhole S and put a bright light source behind it. Okay. So let's take a look at Young's arrangement for producing an interference pattern. Notice the setup in the images. Okay, where light from a single source spread out and reaches two pinholes labeled S1 and S2. This setup is crucial for creating the conditions needed for interference. Okay, so you can see there is S pinhole from which light is coming, and behind S we have placed the light source. Okay, now light from S will reach the S1 and S2, and S1 and S2 will behave as coherent sources. Okay, you can see in the right side of the diagram there is plane wavefronts. Okay, so they are incidenting on two slits, and after incidenting on two slits, so the waves of light are emerging from two pinholes, two slits at the same time. Okay, so at any point on the screen, the phase difference between the waves originating from S1 and S2 slits is either constant or either zero. Zero in the case for central maxima. Okay, we will discuss it. Okay, or you can see in the optical screen front view, there are bright and dark fringes, alternating bright and dark fringes. Okay. So in this arrangement, light spreads out from the first pinhole labeled S and reaches both S1 and S2. This is important because it sets the stage for these 2 points to act as source of light waves that can interfere with each other. Now observe S1 and S2 behaves like two coherent sources. Okay, this means that the light waves coming from S1 and S2 are in phase. Okay, this coherence is essential for creating a stable interference pattern. If the two light sources are not coherent, we cannot attain the stable interference pattern. Okay, for stable interference pattern, so coherence of two sources is essential. So this concept is similar to how two vibrating needles creating matching waves in the water. We have discussed yesterday. Okay, two vibrating or two oscillating needles. We dip the needles in the water at the same time. We take out the needles from the water at the same time. So they are moving in sync. So the waves produced by these two needles were in phase. Okay. So just as those waves can interfere with each other, so too can light waves from coherent sources. Okay. So light waves from coherent sources will interfere with each other. Okay. So this analogy helps us visualize the wave nature of light. Finally, consider how S1 and S2 create spherical waves that spread out in all directions. These waves overlap and interfere, leading to the characteristic pattern of light and dark bands. This is a key takeaway in understanding wave optics and interference. So as we revealed previously, let's focus on what happens when these light waves meet on the screen labeled G'. Okay, they create interference pattern which are a result of the superposition of waves. This is a key concept in wave optics where waves can add up to form new wave. Now let's delve into what these interference patterns look like. They appear as bright and dark stripes, okay, known as fringes. These fringes are a direct result of constructive and destructive interference. Okay, where constructive interference happens or occurs, there is bright fringe. And where destructive interference is occurring, there is dark fringe, where waves either amplify each other or cancel out each other effect. This visual pattern is a hallmark of wave behavior. So finally, we can predict where these bright and dark spots will appear on the screen. The bright spots or area of maximum intensity occurs where the waves constructively interfere, while the dark spots or area of minimum intensity occur where they destructively interfere. Understanding this allows us to precisely determine the locations of these interference fringes. Okay, so let's start by defining some key distances in our setup. We have two slits, S1 and S2, okay, separated by a distance d, small d. The screen where we will observe the interference pattern is placed at a distance capital D from these slits. You can see in the diagram also. Now let's consider a point P on the screen. This point is located at a distance x from the center O. This distance x will help us determine the position of the fringes relative to the center of the pattern. Okay, you can see the center O. Okay, so from source S and from the midpoint of S1 and S2, we will join a line and extend it, and where it touches the screen G dash, that is the center point where central maximum will form. Okay, from that central maxima O, we will take the distance of point P, that is x. Okay, keep in mind that center point O is where the central maxima or brightest fringe is located. Okay, so at this stage, we need to understand how the waves travel from the slits to the screen. Waves from slit S1 travel along the path S1P, while waves from slit S2 travel along the path S2P to reach point P. The difference in these path lengths is what causes the interference pattern. Okay, so now let's considering the path difference. So you can see in the diagram. Now we have modified the diagram. So small d is the distance between the slits and capital D is the distance between the slits and screen. X is the distance from central maxima O to P point. Okay, now we have modified. We have draw a normal from S1 on the S2P. Okay, so angle theta, that is angle S2 S1N, that will be theta also. Okay, so angle between the perpendiculars on, if there is angle theta between two lines, okay, that is between MP and MO, angle is theta, that two lines MP and MO. So the angle between the perpendiculars of these two lines will also be theta. So S1N is perpendicular to MP and S1 S2 is perpendicular to MO. So angle between these two lines S1 S2 and S1N will also be theta. Okay, now we have to this is the path difference delta P. S2N is the path difference. Okay, so S1P and NP, they have same magnitude. So S1P is equal to NP. And what is the extra path? Light is traveling from S2 to P, that is S2N, that is delta P, that is the path difference. Okay, so this path difference is given by expression S2P minus S1P, which we denote as delta P. Understanding this path difference is crucial because it determines the type of interference pattern we observe, whether it's constructive or destructive. So now let's look at the geometry involved in this setup. In the triangle OMP, okay, in triangle OMP, you can see OMP. Okay, we can use basic trigonometry to relate the different components. This will help us derive the expression for the position of the fringes on the screen. So here we introduce the tangent of angle theta. So tan theta, which is the ratio of the perpendicular to the base. Okay, we can say to the opposite side OP to the adjacent side MO, perpendicular upon base. Okay, so this gives us tan theta equal to OP upon MO equal to, what is OP? OP here is X and MO here is D, capital D. So X upon D, where X is the distance from the central maximum to the point P and D is the distance from the slits to the screen. So in this experimental setup, the angles involved are very, very small. So, okay, allowing us to make an approximation for small angles. Tan theta is approximately equal to theta itself. Therefore, we can simplify our equation to theta equal to X upon capital D. Now let's examine the geometry of the setup in the triangle formed by points S2, S1 and Sn. So triangle S2, S1 and N. Okay, we can start analyzing the relationships between these 2 points. This will help us understand how the light waves interfere to create the fringe pattern. So if we introduce the sign of angle theta, sin theta, which is equal to, which is the ratio of perpendicular to hypotenuse, or we can say opposite side to the hypotenuse in our triangle. Opposite side opposite to the theta. Okay, so sin theta is OP upon, sorry, in triangle S1, S2N. So opposite, what is the opposite side of the theta? That is S2N. And what is the hypotenuse here? So we have drawn S1N normal to the S2P. So angle S1N S2, that is 90 degree. So angle side opposite to the 90 degree angle or right angle is hypotenuse. That is hypotenuse here is S1 S2. Okay, so sin theta is S2N upon S2 S1, which is equal to, so what is S2N here? Path difference, delta P. Okay, and D is the distance between the slits, small d, which is S1 S2. So again, small angle approximation. So sin theta is equal to theta itself. This simplifies our equation to theta delta P upon delta T. This approximation is valid because the angles involved in Young's double slit experiment, or we can say the short form for Young's double slit experiment is YDSC, are typically very small. So let's start by introducing 2 key equations, theta equal to X upon capital D and theta equal to delta P upon D. These are the 2 equations. So here theta represents the angle of, so what is the theta? The angle. Okay. So X is the fringe position of screen. Okay, so angle made by ray of light from center of the slits to that P point with respect to horizontal. Okay, so that is theta here. So what is X here? X is the fringe position of screen. D is the distance from the slits to the screen, capital D. And delta P is the path difference. Small d is the distance between the slits. So notice how we can equate these 2 expressions for theta equal to xd, x upon d equal to delta P upon d. Okay. So this equality is crucial because it links the geometric setup of the experiment with the wave nature of light. So therefore, we can express the path difference delta P in a more useful form. Okay, so this step is important because it allows us to calculate the exact position of the fringes of the screen. So path difference delta P is given by equation delta P equal to x d upon capital D. This formula shows us the path difference is directly proportional to the fringe position x and the slit separation small d, and inversely proportional to the distance capital D, that is the distance between the slits and the screen. Okay, so you can see in the diagram, so O point represents the position of central bright fringe. Then after central bright fringe on the both sides, first dark fringe will be formed. After first dark fringe, first bright fringe will be formed. Then after second dark fringe will be formed. Then after second bright fringe will be formed, and so on. That is the alternating dark and bright fringes. On the center, there is a central bright fringe. Okay. So for constructive interference to occur, we have discussed yesterday in the interference that for constructive interference, what should be the path difference between the two waves? So it must be integral multiple of the wavelength, that is n lambda, and n is equal to 0, 1, 2, 3, and so on. So this means that the difference in distance traveled by the two waves should be equal to n times the wavelength, where n is an integer. Okay, so let's relate the path difference to the geometry of the experiment. The path difference denoted as delta p can be expressed as xd upon capital D, where x is the distance from the central maxima, position of central maxima to the point P, and D is the distance between the slits, and capital D is distance to the screen from the slits. For constructive interference, this ratio must equals to n times the wavelength. Okay, so next we determine the position of nth bright fringe from the center. So the formula for position of nth bright fringe, that is xn, is equal to n lambda capital D upon small d, where n is equal to 0 plus minus. Why plus minus? Plus for bright fringe on the upper side of central bright fringe, and minus for the bright fringe in the lower part, in the lower side or downward side of the central bright fringe. On the both side of central bright fringe, there are other secondary bright fringes. Okay, so that's why plus minus. Plus is for upward and negative is for downward downward bright fringe. Okay, so for n equal to 0, position x naught, that is position of central maxima, is also 0, which corresponds to central bright fringe. This is the brightest spot and is located directly in the middle of the pattern. Okay, so let's recall the condition for dark fringes, which is the result of destructive interference. This occurs when path difference between the two waves is an odd integral multiple of half the wavelength. This is crucial because it determines where the dark fringes will appear on the screen. So the path difference must be an odd integral multiple of lambda by 2. So it is expressed as delta p equal to 2n plus 1 lambda by 2. So 2n plus 1 is the odd integral multiple. If we put 0 here, it will result in 1. So it will be 1, odd integral multiple. And if we put 1 here, n equal to 1, it will become 3. That is also odd number. So odd integral multiple of lambda by 2. So this means, what is delta p? We have calculated xd upon capital D. Okay, so this condition translates into equation xd upon capital D equal to 2n plus 1 lambda by 2, where x is the position of the dark fringe. Okay, D is the distance between the slits, capital D is the distance from the slits to the screen. So therefore, position of nth dark fringe from the center can be calculated as xn equal to 2n plus 1 lambda capital D upon 2D after rearranging. Okay, so xn will be 2n plus 1 lambda capital D upon 2D after rearranging the above equation. Okay, so where n equal to 0, plus minus 1, plus minus 2, or so on. Okay, so we use the minus sign, then n plus minus 1 gives us the first dark fringe on the both sides of central bright fringe. Okay, so if we are using plus sign in 2n plus 1, okay, then n equal to 0 gives the first dark fringe. Okay, if we are using 2n plus 1, then if we put n equal to 0, then it will become 1. 2n plus 1 become 1 if we are putting n equal to 0. So x0 will represent the position of first dark fringe, that is lambda capital D upon 2D. Okay, if we are using negative sign in 2n plus 1, okay, so it will become 2n minus 1. Okay, because in some questions you will face when you will solve from different books, or in different books, it is written, somewhere it is written 2n plus 1, somewhere it is written 2n minus 1. If you are using 2n plus 1, then n will be started from 0. For first dark fringe, n will be 0. But if it is written 2n minus 1, then first bright fringe will be, first dark fringe will be from n equal to 1 or plus minus 1. Okay, so if there is 2n minus 1, if you put n equal to 0, it will become minus 1. So minus 1 is not any position. Okay, so you will have to put plus minus 1. If in any question or in any book it is written 2n minus 1 in the place of 2n plus 1, then first dark fringe will be given by n equal to plus minus 1, gives the first dark fringe. Okay, so let's define what fringe width means. So what is fringe width? It is denoted as beta. Okay, is the separation between two consecutive bright fringes or two consecutive dark fringes. Okay, notice the image here which visually represents these fringes. Okay, so distance between or separation between two bright fringes or the separation between two dark fringes is known as fringe width. Okay, so now let's focus on the bright fringe width. The separation between two dark fringes will give us bright fringe width. Okay, separation between two dark fringes. So in between two dark fringes, there is a bright fringe. So separation between two dark fringes will give the width of bright fringe. And separation between two bright fringes will give the width of dark fringe. Because dark fringe is between two bright fringes. So separation between two bright fringes will give the fringe width of dark fringe. Okay, so this is because the dark fringes act as a boundary for the bright fringes. And bright fringes act as boundary for the dark fringe. Okay, help us measure their width accurately. Okay, separation between two bright fringes will give us the dark fringe width. This relationship is important because it shows a symmetry in interference pattern. White bright and dark fringes alternate regularly. So let's look at the formula. So fringe width is given by equation beta equal to xn plus 1 minus xn. Okay, where xn plus 1 and xn are the position of consecutive fringes. So xn plus 1 represents the position of one fringe. Okay, either dark or bright. Okay, and xn represents the position of another fringe just before the xn plus 1 fringe. Okay, so it is representing the position of two consecutive fringes, either bright or either dark. So understanding this formula allows us to calculate the exact spacing between the fringes. So let's start by looking at the position of nth dark fringe. It is given by the formula xn dark, which is equal to 2n plus 1 lambda capital D upon 2D. Okay, so what is the fringe width of bright fringe? So we want to calculate the bright fringe width denoted by beta bright. So it will be the separation between two consecutive dark fringes. Okay, so that means we can found using the formula beta bright is equal to xn plus 1 dark minus xn dark. So these are two consecutive dark fringes, and difference between the position of these dark fringes will give the fringe width of bright fringe. Okay, so beta bright will be equal to, so let's substitute the expression for the position of dark fringes into a formula beta bright. Okay, so we have beta bright is equal to 2n plus 1 lambda capital D upon 2D, because position of dark fringe is represented by 2n plus 1 lambda capital D upon 2D. So here n is n plus 1. So put n plus 1 in place of n. So 2n plus 1 lambda capital D upon 2D minus xn dark. So xn dark is 2n plus 1 lambda capital D upon 2D. This shows us how the position of consecutive dark fringes are used to find the bright fringe width. So simplifying the expression further, we get beta bright equal to, so after simplifying it is 2n plus 3 lambda capital D upon 2D. So separating it, the second term, it will become 2n lambda capital D upon 2D minus lambda D upon 2D. Okay, so now 2n in the first term, that is 2n plus 3. So we will separate it also. So 2n lambda D upon 2D will cancel out with minus 2n lambda D upon 2D, and 3 lambda D upon 2D minus lambda D upon 2D will become 2 lambda D upon 2D. Okay, so finally after simplifying we arrive beta bright is equal to 2 lambda capital D upon 2D. Okay, so 2 and 2 will get cancelled out. It will be equal to lambda capital D upon D. This is the formula for bright fringe width in the Young's double slit experiment. Okay, so let's take a recap. So in YDSE, bright fringe width is given by lambda capital D upon D. This formula helps us understand how the interference pattern is formed and how the spacing between the fringe widths is determined. Now to calculate the dark fringe width. Okay, so let's start looking at the position of bright fringes. So position of nth bright fringe is given by formula xn bright is equal to n lambda capital D upon D. Okay, so here n is the fringe order. Okay, so bright fringe position is given by that. Now we have to find the fringe width of dark fringe. Okay, so dark width of dark fringe is given by separation between the two consecutive bright fringes. So let's move on to the finding the width of the dark fringe. This is an important step because it helps us understand the spacing between the dark and bright fringes in the interference pattern. Okay, so dark fringe width beta dark can be calculated using difference between the positions of consecutive bright fringes. So beta dark is equal to xn plus 1 bright minus xn bright. That are the position of two bright fringes. Okay, one after another. This shows that dark fringe width is essentially the gap between the two bright fringes. Okay, now put n plus 1 for the first term in the formula n lambda d by d. So in the place of n, we will put n plus 1. So beta dark will be equal to n plus 1 lambda capital D upon D minus xn bright will be n lambda capital D upon D. Okay, so n terms will get cancelled out and beta dark will be. So after simplifying, we find beta dark equal to lambda capital D upon small d. This tells us that the width of the dark fringe is directly proportional to the wavelength and distance to the screen and inversely proportional to the slit separation. So width of the bright and dark fringes in Young's double slit experiment is the same. Okay, we calculated and it came out to be same, which is lambda capital D upon D. This symmetry in fringe width is a key takeaway from our discussion in wave optics. Now we are going to explore the fascinating world of wave optics, okay, focusing on computer generated fringe patterns. Notice the image on the slide which shows a pattern produced by 2-point sources S1 and S2 on a screen. This setup is classic example of how wave interference can be visualized. Okay, pay attention to the parameters. The distance between the sources D is 0.025 millimeter. That small amount of distance. It is 0.025 millimeter. That is 25 micrometer. Can you imagine that distance? Very, very small. Okay, so the distance to the screen, capital D, is 5 centimeter and wavelength is 5 into 10 is per minus 5 centimeter. Okay, so these values are crucial for understanding the pattern we see. And one thing to note, that actual fringe shape of in Young's double slit experiment is parabolic. It is not rectangular, exactly rectangular strips. It is not like exactly rectangular. It is slightly parabolic. Slightly parabolic. That means slightly curved. Okay, it is not exactly straight. So let's examine the alternating bright and dark fringes known as fringes in the pattern. These fringes are a direct demonstration of the wave interference phenomenon. When waves from the two sources meet, they can either reinforce each other or cancel out each other. Either constructive interference occurs, either destructive interference occurs, leading to these distinct bands. This is the fundamental concept in wave optics, illustrating how waves interact in space, where the bright fringes represent the constructive interference. Okay, and the waves from two sources add up to create a brighter intensity. In contrast, the dark fringes are the areas of destructive interference where the waves cancel out each other, resulting in darkness. This interplay between constructive and destructive interference is key to understanding many optical phenomena. So now let's summarize what we have studied today. So Young's double slit experiment is crucial because it demonstrates the wave nature of light. Therefore, through interference patterns, two slits S1 and S2 separated by a distance d. When light passes through these slits, it creates an interference pattern on a screen. The path difference denoted by delta P is given by formula delta P equal to xd upon capital D, where x is the distance from the center of the screen, d is the distance between the slits, capital D is the distance from the slits to the screen. So condition for bright fringes, which are bright bands you see on the screen. For a bright fringe, the path difference must be integral multiple of wavelength. So delta P equal to n lambda. The position of bright fringes is given by xn equal to n lambda capital D upon small d, where n equal to n can be 0, plus minus 1, plus minus 2, and so on. For dark fringes, which are the dark bands between the bright ones, for a dark fringe, the path difference is given by delta P equal to 2n plus 1 multiplied by lambda by 2, means odd integral multiple of lambda by 2. The position of these dark fringes xn equal to 2n plus minus. Why we are using 2n plus minus? So I have mentioned either it can be plus, either it can be minus. So you have to choose the n value accordingly. If it is 2n plus 1, then n value will start from 0. So n equal to 0 will represent the first dark fringe position. And if 2n minus 1 is there, then n equal to 1 will represent the first dark fringe position. So this formula help us find where the dark spots will appear, completing the understanding of our interference pattern. So continuing with the summarized points, fringe width refers to separation between the consecutive fringes in an interference pattern. The formula for the fringe width is beta equal to lambda capital D upon small d, where lambda is the wavelength of light, capital D is distance from the slits to a screen, and d is the distance between the slits. All interference fringes have equal width regardless of their order. This means that the spacing between each bright or dark fringe remains consistent across the pattern. This uniformity is a key characteristic of interference pattern. Two independent sources like sodium lamps do not produce an interference pattern because they are incoherent sources of light. Coherence means that the light wave maintain a constant phase relationship, which is essential for creating stable interference patterns. The central bright fringe, where n equals 0, occurs at x equal to 0 on the screen. The entire interference pattern is symmetric about its central bright fringe. This symmetry helps us predict the position of other fringes on the screen. Now here are some questions based on what we have studied today. In Young's double slit experiment, if the distance between the slit is doubled while keeping the wavelength and screen distance constant, the fringe width will become of its original value. Okay, so what is the... So you have to fill in the blank. So fringe width will become how much times of its original value. Okay, and this is about how this affect the pattern. Okay, so we know that fringe width depends on which quantities. Is it depend on wavelength? Is it depend on slit separation? Is it depend on screen position with respect to slits? Okay, so you have to write the formula and then derive the relation. And if slit slit separation is doubled, then what is the effect on fringe width? You have to write it. So calculate the fringe width when we have specific values, given that the wavelength lambda is 600 nanometers, the distance of the screen d is 2 meters, and distance between the slits small d is 0.2 millimeter. Okay, so you have to calculate the fringe width beta. Now let's determine the order of bright fringe. Okay, for the nth bright fringe, we have x equal to 0.3 centimeter, capital D is capital D is 100 centimeter, small d is 0.05 centimeter. So what is capital D, small d we have discussed. Okay, lambda is equal to 5000 angstrom. What is angstrom? 10 is per minus 10 meter. So use the formula for the position for nth bright fringe. So solve for n to find which bright fringe correspond to this position. Okay, so for the third dark fringe, we need to find the path difference. Okay, so calculate. So what is the formula for path difference for the dark fringe? Okay, now you have to calculate the path difference for n equal to 3. So what happens when we increase the wavelength by 20% while keeping the small d and capital D constant? So what will be its effect on the fringe width? So fringe width will increase by what percentage if we are increasing the wavelength by 20%? Okay. So this is all about today's lecture. I hope you enjoyed the session and understood it well. So thank you.